Hello guys, how are you today? So today I'll be explaining the physics 6.1 to the 6.5 course practice, okay? So let us start with the first question. In the first question, they said drag and drop the correct terms from the box below. Sound can be defined as a what wave motion since it is what and it needs a what to travel through. First of all, we know that sound can be defined as a longitudinal or longitudinal wave motion. Why? Because it moves along the same direction of propagation. If you want to test it out, you could take a candle, okay? And you could start talking in front of the candle, not in such an intensity to blow it out, but just like talk in front of the candle, and you'll see that the candle moves back and forth. It does not move up and down. If it moved up and down, that means that sound can be defined as a transverse wave motion, but since it moves left and right and it is moving along the same direction of propagation of the wave, then that means that sound is a longitudinal wave motion. Okay, it is also what? It is mechanical. Why is it mechanical? Because it needs a medium to travel through. If you go to space without a helmet or without like walkie-talkies, you will not be able to hear the other person because in space it is vacuum. There's no medium. So if you scream, no matter how hard you scream, you will not be heard because there is no medium for the sound to travel through. Okay, we move on to question number 2. In question number 2, it says, a water wave can be generated by continuously tapping on the water surface, as shown below. This shows us that waves are vibrations because you're touching it, you're causing a vibration, and this vibration will transfer what? It will transfer energy from place to place without matter being transferred. So, for example, the candle, like wave, when you're talking, it is a vibration. The vibration is happening in your vocal cords. Your vocal cords will start to vibrate. They will cause sound. This sound will transfer the energy, okay? And this energy will be the sound energy, and it will go from place to place. And with the candle, is the candle moving? No, it's just moving back and forth along the wave of propagation, or along the direction of propagation of the wave. But as you can see, the candle, it's not it's not gonna be moving with your voice. So if your voice is gonna be from here until the end of your room, the candle is not gonna move from here all the way until the end of your room. Okay, so we will move on to question number 3. In question number 3, they told us, define the mentioned regions, fill in the blanks. When particles of the medium are spread out, we call this rarefaction. Okay? However, when particles of the medium are closest together, we will call this compression. Now, the diagram below shows the variation of the pressure of a sound wave in air at one instant with respect to the distance. So what you need to know is that the one with the least amount of pressure, this is what? This is where rarefaction occurs. And then the one with the most amount of pressure, which is over here, this is where the compression will occur. Okay, so they said which point represents in rho A. Rho A is rarefaction. So if we are dealing with rarefaction, we'll have to take the lowest pressure, which is Z. Okay, which point represents the description in rho B? In rho B, it is compression, so we'll have to take the highest pressure, which is X. Okay, we'll move on to question number 4. In question number 4, they said match each term to its description. First of all, what you need to know is that frequency is the number of waves per second, speed is distance over time, wavelength is the distance from crust to crust, or trough to trough, or from starting point to ending point, but not like 0, you skip 1, then 0 again, and then amplitude is the maximum distance from the resting position, or from 0. So amplitude, it's the maximum displacement of particle from its rest position. Speed, it is what? Speed is the distance over time, the distance traveled per unit time. Frequency is the number of waves per second, or the number of cycles completed per second. And then finally, the wavelength is the length from one peak to the next, or from crust to crust, or from trough to trough. Okay, we move on to question number 5. Consider the 4 diagrams below, plotted using the same scale A, B, C, and D. Alright, Which graph is the loudest? Usually the loudest graph has to have the highest amplitude. The highest amplitude is the one with wave B, because as you can see, graph B has the highest amplitude. Okay? And then they said which one has the highest pitch? The one with the highest pitch has the highest frequency, or the most number of waves per second. Let us assume all of this is 1 second. Okay, if that's the case, then D will have the highest frequency, so then consequently it will have the highest pitch. We move on to question number 6. A wave in which displacement of particles is along the same direction of the wave's propagation is called a longitudinal wave. Whereas if we are dealing with a transverse wave, okay, then the object will be moving perpendicular. Okay, so an example of a transverse wave would be what? It would be a rope. So if you take a rope and you start, like you hold it from one side and another side, and you start to move it up and down, you will see that the waves will be created like this. Wait, hold on. Something like this, yeah? And if you, for example, tied a hair tie over here, let's say this is the hair tie, and you continue moving it, you will see that the hair tie will not move like this. It will not go forward and backward. No, it will go up and down, and then up and down. And because it's going up and down, this is just indication that it's what? That it is perpendicular, and that it is a transverse wave. Okay, we move on to question number 27. In question number 27, they said the wavelength of a wave is 25 centimeters and its frequency is 12,000 hertz. They need the speed of this wave in meters per second. Speed is equal to what? It is equal to the wavelength, which will denote by lambda, times the frequency f. What is the wavelength? We need to change it into meters. So the wavelength is 25 centimeter, which is 0.25 meter, times the frequency, which is 1200 hertz. Let us put it on the calculator. 0.25 times 1200 hertz, you will get that it is 300 meters per second. We move on to question number 8. In question number 8, match each term to its corresponding description. A train of pulses is definitely a wave. A disturbance traveling through a medium is definitely a pulse. And then the point along the wave corresponding to the maximum displacement of particles in the longitudinal wave. The maximum displacement of particles means the farthest possible the particles are away from each other, which is rarefaction. We move on to question number 9. In question number 9, they said, which of the following describes a sound wave in air? We know that a sound wave, first of all, it is longitudinal. So that means the wave, any object will, when it's coming across the wave, it will move along the wave. So in a direction along the wave. For example, you can try it with a candle. You can talk, you'll see the candle is moving back and forth, but it's not moving up and down. If it was moving up and down, that means that it is a transverse wave. It is also a mechanical wave because it needs a medium to propagate through. Okay, now we move on to question number 10. In question number 10, they said the diagram below shows the displacement of soil during the propagation of a wave along the surface of the earth after an earthquake. What kind of wave is shown in the diagram above? You can see what? That the motion, it is along the wave, along the direction of the wave. So because it is along the direction of propagation of the wave, it is what? It is longitudinal. So it is, first of all, a longitudinal, and second of all, it is a mechanical wave. It's definitely not an electromagnetic wave. Why? Because it needs a medium to travel through. That's why it's a longitudinal mechanical wave. We now move on to part B. In part B, they said, underline the points at which compressions are observed and circle the points at which rarefaction is observed. Compressions will be observed at points 1 and 3. You can see that the particles are so close together. Okay, so 1 and 3 is compression. Whereas rarefaction, you can see that it is happening at 2 and 4 and not 5. 5, they are all constant, whereas 2 and 4, they are larger than usual. So very simply, that is it. You can even click on 5, you'll see there's no need to click on it. Now here, this is something very interesting. We know, first of all, that the speed of sound in water versus the speed of sound in air. We know, first of all, that sound is what? Sound is a mechanical wave. That means it needs a medium to pass through. And if it needs a medium to pass through, that means the denser the medium the heavier the medium is, then the faster its speed is gonna be. That means the speed of sound in water is greater than the speed of sound in air. It's the opposite for light. Light is an electromagnetic wave, so it does not need a medium to travel through. It can travel in vacuum. So that means the less dense or the lighter the air, the medium of propagation is, the faster the speed of light will be. So in this case, the speed of light in water is greater than the speed of light in air. Now, in all cases, if we are talking about in the same matter, of course, the same matter of propagation or the same medium of propagation, then the speed of sound, okay, it is less than the speed of light, if they are both in water, of course. So keep this in mind. When we're comparing speed of sound and speed of light, then definitely the speed of light is faster than the speed of sound in water. Now, the speed of infrared radiation in air versus the speed of visible light in air, these are equal. If they are in the same medium, okay, then any electromagnetic wave will have the same speed. So remember, if they are in the same medium of propagation, then any electromagnetic wave will have the same speed. And we move on to question number 12. They told us satellite laser ranging uses short pulse lasers, powerful light sources, and sensitive timing devices to measure the distance to the satellites orbiting the Earth. The laser pulse is emitted from Earth, reflects from the satellite, and it was detected by a sensitive sensor on the ground. The laser signal returns to Earth 1 times 10 to the power of minus 2 seconds after it was emitted by the laser. The wavelength of the electromagnetic radiation used is whatever. The speed of light is 3 times 10 to the power of 8 meters per second. They want us to find the altitude of the satellite above Earth's surface. So let's take it like this. We have that in 1 times 10 to the power of minus 2 seconds, look what happened. We have that the signal was sent, it reached the satellite, and then it bounced back. So all of this happened in what? 1 times 10 to the power of minus 2? Is it that? Yeah, minus 2 seconds. And we know that the speed of light is how much? The speed of light is 3 times 10 to the power of 8 meter per second. So to find the altitude, what are we gonna do? We are gonna multiply, first of all, the speed of light, 3 times 10 to the power of 8 meters per second, by what? By the time, which is 1 times 10 to the power of minus 2 seconds, but divided by what? Divided by 2. Because all of this multiplied together, it is the value of going up and returning. But we need only the distance of one of them. So to find the distance of one of them, or the actual distance, which is only from the satellite to the receiver, then we are going to divide it by 2. So let me get my calculator. Okay, so with the calculator, you are going to solve it. It's 3 times 10 to the power of 8 times 1 times 10 to the power of minus 2 over 2. Okay, now you will get an answer which is 1500000. Okay, if we go down, we will see that they want it in kilometers. So to change it into kilometers, you will divide by 10 to the power of 3, and you are going to get 1,500 kilometers. Now, they said, what is the primary reason for using the electromagnetic waves instead of sound waves in this method? Because we know sound waves cannot travel through vacuum, whereas electromagnetic waves can travel through empty space, which is the vacuum. Okay, we move on to question number 13, my bad. The diagram below shows the displacement time graph for a longitudinal wave in a slinky. Okay, so look what's gonna happen over here. We are given what? We are given the diameter, I believe, in centimeters, and the time in seconds. They want the period of the wave. To find the period of the wave, first of all, what is period of the wave? The period of the wave, it is how long it takes one wave to pass. So to do that, what are we gonna do? We are gonna, first of all, take 2 crests. So let us say, for example, we chose 2 crests. We chose this crest over here, which is approximately 0.1, and this crest over here, which is approximately 0.5. So 0.5 minus 0.1, you will get the period of one wave to move. You could do it like this, or you could take it like this. You will see that, okay, this is the line where the waves start and finish. Let me do it again. Okay, one wave will start here and it will finish over here. So you will come to this time and you will see that it is 0.4 seconds. So very simply, the period of this wave is 0.4 seconds. Now, the frequency is what? The frequency is how many waves can there be in 1 second. So what are we going to do? We're going to go 1 second and we're going to see that it stops over here. And based on, if we draw the line, okay, we will see that it is 1 wave, 2 waves, and half a wave. So the frequency is 2.5 waves because this is 1 wave. Okay, this over here is 1 wave. Then this over here is another wave, and then this one over here, it is half a wave. So it is 2.5 hertz. The frequency is then 2.5 hertz. We move on to the last question, which is the amplitude of the wave. The amplitude is the highest point of the wave. So if you estimated this is 1.2 centimeters. So that is it for question number 13. We move on to question number 14. In question number 14, they said the diagram below shows the displacement of the rope as the wave propagates through it. Remember, we said that the wave propagating in a rope, remember, if we tied a hair tie on the rope and we moved the rope, it would move up and down. That means it's perpendicular, and if it's perpendicular, then it is transverse. First of all, that means it's either transverse mechanical or transverse electromagnetic, but for sure it is transverse mechanical. Why? Because the wave needs a medium to pass through. Okay? We move on to part B. Choose the correct answer to complete the sentences below. The wavelength of the wave. Let us choose the wavelength together. Okay? You have many ways to find the wavelength. The first way is either like this. You can take it from crest to crest. So from here till here, and you will calculate approximately the distance. Or you can take it from 0, skip this 0, take this 0 over here. It's approximately 0.63. Or you can take it from trough to trough, and then you can estimate it. But the most accurate is to take it from 0, skip this 0 and 0 over here. You will get it as approximately 0.63 meters. Now they need the amplitude of the wave. The amplitude of the wave is always the highest point. So as you can see, this is the amplitude of the wave, which is 20 centimeters. However, they need it in meters, so 20 centimeters. To change it to meters, you're going to divide by 100, and you will get the answer to be 0.2 meters. Okay, so the answer over here is 0.20 meters. We're going to move on to question number 15. Match each term to its corresponding definition. Now here they want us to match. My bad, I apologize for that sound. Okay, we move on to question number 15. In question number 15, they told us match each term to its corresponding definition. The rate at which the wave carries energy through the unit area at right angle to the direction of travel. Here, let's say this did not make sense to us. Okay, so let's leave it aside. Okay, we'll move on to the next one. A property of wave that depends on the frequency of the sound. Frequency is directly proportional to the pitch. The property of wave, or the property of sound, determined by the wave amplitude. Wave amplitude is directly proportional to the loudness, and this leaves us with sound intensity to be the last one. Now, another thing you should know is loudness is directly proportional to amplitude, pitch is directly proportional to frequency, and the sound intensity is directly proportional to the amplitude squared. So which property changes the frequency? It is the pitch. Which property changes when the amplitude is increased? It is definitely the loudness of a sound. And now finally, the amplitude of the sound wave is doubled. We know that. The sound intensity, it is directly proportional to the amplitude squared. So if the amplitude is doubled, so it becomes 2 amplitude. So now you'll have to square it. Then it's going to be 4 amplitude squared. And then you would have to what? You would have to multiply the sound intensity by 4. So very simply, the amplitude of the sound wave is doubled. How does the intensity of the sound change? It is quadrupled. My bad, it's not doubled. It is quadrupled. So it is multiplied by 4. So let us submit, and hopefully we do not have any mistakes. And thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day. I'm gonna wait for it to load. Yeah, no mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day.